Hello everyone, welcome to the week 11 problem solving session for the pattern recognition and application course. I am Tanuka from IISc. I am a PhD student over there in the electrical engineering department. So in today's session we will solve some problems on SVM as well as some clustering algorithms. The first set of problems that we have are on SVM. So before going into the problem, let's briefly revise what SVM was. So SVM was also a type of classifier, and in this particular type of classifier, what you do is, while deciding the decision boundary which will separate your classes, let's say we are considering two class problem, then the decision boundary separating the two classes that you will have to determine, which will be your discriminant function. While choosing that, you choose it in such a way that you get the maximum margin from both the classes. So you pass it through such a such a way that the distance of the closest points from one class to the decision boundary and that of the other class, those are equal and those will be as large as possible. So when you have a large margin involved in the designed classifier, then the benefit is there is a lower chance of getting misclassified data. So if you have a large error margin, then even if one data point from one class is slightly perturbed due to some noise or some measurement error or something, so it's less likely that it will cross the boundary and go to the other side if you have a large margin. On the other hand, if you have a very small margin, then you can get slight perturbation or you can make a small error in measurement. In case of real world problem, you can have a small error in measurement and your data point will be misclassified into the other class. So it's very prone to getting misclassified if you have a very less margin. Even if even after that there might be some points which are apart from this training data, some point may come up which are even closer to the boundary. For that case also, if you have a larger boundary, you have more room for those to get correctly classified. So the risk involved is much less. So you are at a more safer, your points are at a more safer place, it will not easily get misclassified. So that is the idea behind this SVM classifier, which is trying to maximize the margin with each class and the decision boundary. Okay, and when you try to solve this SVM problem or SVM classifier design, when you do, then you see that the decision boundary that you finally get is not dependent on all the training data points that you have. Okay, so it's just dependent on some of the points from both the classes which are closest to the boundary, which are closest to the decision surface, basically which are at the boundary of the two classes. Those are important in making the decision surface. The other vectors which are at some inside the two classes, which are not towards the boundary, which are towards the inner part of the classes, those are not making such contribution. They do not have any contribution in deciding what will be the decision boundary. So the only feature vectors which are at the boundary of the two classes, they will itself determine where the decision surface should pass through. So this is a very popular classifier used for any machine learning problem. So let us try to solve some problems based on this SVM classifier or support vector machine. So the problem that we have is for a two class problem shown in figure, which are the support vectors for an SVM classifier. So, in this figure it is, as you can see, the features that you have for each training data point, those are 2D features. So, we have plotted them in the xy plane. Let us say the first feature dimension is x and the second feature dimension is y. Now, the blue points that you have, that belongs to one class, and the red points that you have, those belong to the other class. Red belongs to class 1 and blue belongs to class 2. Now, the question is, if you train a support vector machine to do a classification of these two classes, then what will be the, which will be the support vectors? So, as you can see, this is one class and this is another class. So, for you to separate the two classes, the decision boundary should pass between these two somewhere at some orientation. It should pass between the two classes so that it can separate the two. Now, if it passes through such a region, you can see that the first let us see the red class. You can see that this point is definitely closer, it will be closer to the decision surface as compared to all the other points, right. All the other points are much far from the decision surface. May that decision surface that I have drawn here may not be the exact one, it may have slightly different orientation, but it will pass somewhere between the two classes. So, since this particular red point is much closer to that region, so always it will be the closer one for the decision surface. So, from class 1 this will be the support vector. Now, from class 2 you can see both this and this, both are closure, and you can see if you carefully see the graph, the two of these points lie on a straight line. Okay. You can so these two are on a straight line, and anyway they will be on a straight line, the 2 points, but that this is a particular straight line which is the boundary of this decision surface. There is no more point outside this particular straight line. Okay. So, you can see that the decision boundary that you will get, these 2 points will be the closest, since that the line passing through these 2 points is the boundary of that particular class. So, the decision surface that you will get, that will be somewhat parallel to that line. So, both of these points will be equidistant to that decision surface. So, from the blue class, both these points will become the support vectors. So, together considering both the classes, we will have 3 points, 1 from the red class and 2 from the blue class, which will act as the support vectors. And if you have to note down the coordinates, it will be 4, 3, which is the red point, and the other two are 4, 5 and 7, 2. So, these 3 will be the support vectors if you have this particular training data set. Okay. And the remaining ones will be always much far from the decision surface as compared to these 3. Okay. Now, once we have determined that, the next question is, what is the equation of the decision surface? So, as I already told, the straight line joining the 2 blue points. So, this is the straight line joining the 2 blue points. So, this is the boundary for the blue class. Similarly, you can have one boundary for the red class, which is parallel to this line and passing through the red point. So, these are the 2 boundaries. So, the support vectors are lying on these 2 particular straight lines, and these 2 are parallel straight lines. Now, if you have to have a decision surface which maximizes the distance with support vectors from both the classes. I am saying the distance between only for the support vectors, because the others do not finally matter. If you have maximized the distance with support vectors, then that will work. So, you will have to have a decision boundary which will be having maximum distance from the support vectors of both the classes. So, that will be the case if your decision surface is parallel to these two boundary lines, and that is equidistant from both these lines. So, kind of passing halfway between the two lines. Okay. That will be having the maximum distance, because you know the distance when you have to have the maximum distance from both sides, then you will have to divide it at the middle. So, for determining the equation of that particular decision surface, let us first try to write the equation of these two boundaries. Then we can simply tell that the line in which is equidistant from these two, which is the perpendicular bisector of these of the distance between these two straight lines, that will be the decision surface. So, if you first see the boundary of the blue class, so the boundary straight line will pass through 2 points which we have already mentioned as 4, 5 and 7, 2. So, it will pass through 4, 5 and 7, 2. So, if you write the equation of that straight line, that will be y minus y1 by x minus x1 minus y1 minus y2 by x1 minus x2. Three minus 1. That gives you y minus 5 equals to 4 minus x, that is y equals to minus x plus 9. So, the equation of the boundary of the blue class, this one, is y equal to minus x plus 9. Now, the boundary for the red class, the straight line that we have, that is parallel to the boundary of the blue class. So, the slope of the line will be same as that of the boundary of blue class, but only the intercept will be different. So, we can say that the equation will be, this is for blue class, for red we can say the equation will be, since the slope is same, so y equal to minus x is same plus some intercept c. Now, this is passing through the support vector 4, 3. This is passing through 4, 3. So, if you put that, then you get 4 equals to minus 3 plus c, which gives you c equals to 7. That means, your final equation will be y equal to minus x plus 7. So, this line is y equals to minus x plus 7. Okay. So, these are the two boundaries. Support vectors from the two classes are lying on these two lines. So, now you will have to find the straight line which is parallel to these two lines and equidistant from these two lines. That will be your equation of the decision surface. So, you can easily see that the decision surface will be, so that will be parallel. So, the slope will be the same and it will be the perpendicular and it will be equidistant from both. So, it will be midway. So, the equation will be y equal to minus x plus 8. The slope is same because it is parallel to both the boundaries, and the intercept is different because it has to be it is midway between the other two, because it is equidistant from both the surfaces. So, this is your final decision surface equation, and it will pass somewhere like this, somewhere like this. Okay. Now the next question arises is, find the margin using SVM. So, in case of SVM, what is the margin? Margin is basically the distance of the support vectors, any of the support vectors from the decision surface. So, if you have to, you are actually maximizing this margin in case of SVM. When you are trying to determine the decision boundary, you are trying to maximize this margin. This is basically the distance of the support vectors, any of the support vectors from the decision surface. So, to find that, we already know the equation of the decision surface is y equal to minus x plus 8. Now, we can choose any of the support vectors because all are equidistant from the decision surface. So, we can choose any of it and find that point's perpendicular distance from this particular line. That will be our margin. Let us choose this point. Let us choose this one. We are taking this point. So, this is 4, 3. Now, we need to determine the distance of this point from the decision surface or from the line y equal to minus x plus 8. For that, let us rearrange the equation and take all the terms on one side. So, that will make it x plus y minus 8 equal to 0. If you have this equation, then you know to find the distance, perpendicular distance of any point from this line, what you will have to do is, you will have to compute the value of x plus y minus 8 at that point and divide it by the root over of coefficient of x square plus coefficient of y square. So, here if you put x equal to 4 and y equal to 3, your distance will be 4 plus 3 minus 8 divided by coefficient of x is 1. So, 1 square plus y is also 1. So, 1 square. So, that becomes minus 1 by root 2. And since this is the distance, it will be the magnitude of this. So, magnitude of this you take 1 by root 2. So, this is your margin. The margin of your SVM classifier will be 1 by root 2. Now, the next question is, classify the unknown point 5.23 using this SVM. So, again the decision surface that we have is minus x plus 8. So, or you can write it as we wrote last time, x plus y minus 8 equal to 0, right. So, this is the equation of the decision surface. This is somewhere here. This equation is y equal to minus x plus 8. Now, if you, so one side of this equation will have positive values of x plus y minus 8 and one side will have negative values of x plus y minus 8. So, if you just put one point and check which side is positive, let us put this point which is 7 2. If we put, then we will get 7 plus 2 minus 8, that is equals to 1. So, which is greater than 0. So, this side is greater than 0, means this side is less than 0, and on the straight line it will be equal to 0. This is the value of x plus y minus 8. So, let me write it more clearly. On the straight line you have x plus y minus 8 equal to 0. This side you will have x plus y minus 8 greater than 0. This side you have x plus y minus 8 less than 0. Okay. Now, for the unknown point, again you will have to compute the value of x plus y minus 8 and see whether it is positive or negative. If it is positive, then it belongs to the blue class, which is class 2, and if it is negative, it belongs to the red class, which is class 1. So, the point that we have is 5.23. So, if you put that, you will get 5.2 plus 3 minus 8. that will be equal to 0.2, which is greater than 0. So, greater than 0 is this particular side. So, this particular point will be classified into the blue class, which is class 2. So, the point 5.23 will belong to class 2 according to this decision surface determined by the SVM classifier. Okay. I hope this is clear to everyone. Now, the next question that comes is, will the decision surface using SVM change if one more data point from class 1, sorry, this will be class 2, I am sorry for the error, this will be class 2. Will the decision surface using SVM change if one more data point from class 2 is at 6, 6. So, this is 6, 2, 3, 4, 5, 6, that means you have one more point over here, one more blue point over here. If there is one more blue training sample or class 2 training sample at the point 6, 6, then will the decision surface change or not? So, anyone would like to answer? Will the decision surface change if you have one more training sample, or will the decision surface be the same as before? What do you think? Can anyone try? What do you think? Will the decision surface change if you add one more point 6, 6, which is far inside the data set and not towards the boundary of this particular class with the other class, not towards that part, it is far inside the class. Yeah, Siddharaj is saying it will remain the same. You are correct, it will remain the same, because the decision surface that you are determining, as I said, it only depends on the support vectors, not the data points which are inside the class. So, if I am adding one more data point inside the class, that will not hamper or that will not change what the decision surface that we had. So, this will remain the same. Now, let us say we have the data point at 6, 2, which is over here. In this case, you see you have got one more data point that is now at the boundary. So, now the boundary is this for the blue class. This is passing through the new point. Yeah. So, previously this point was on the decision boundary, and this point was on the boundary of this particular class, sorry, not the decision boundary of this class. Now, since you have got one more point which is closer to the other class than this particular point, so now this is forming the boundary. So, now the equation of your boundary has changed, your support vectors have changed. Now, if you try to determine your decision surface, that will certainly be changed, because your decision surface depend on the support vector. So, initially you had to maximize the margin with the support vectors this and this margin. You have to compute the margin with these 3, and you have to, your optimization problem is to maximize the margin with these 3. So, it will be equidistant between the straight lines passing through these support vectors. Now, your support vector has changed. So, now you will have to maximize the margin with the new set of support vectors. So, certainly your decision surface will now change. Okay. So, the answer is it will certainly change. So, you see that when you are adding a training sample which is inside the class, which will not become the support vector, then adding that training sample does not make any change to the learned decision boundary. But you are adding one training sample so that that will become the new support vector, then the equation of the decision surface will be changed. So, these were a complete set of problems involving all the concepts of SVM. So, I hope that is clear to everyone. If you have any question, you can ask at this point. Then we will move on to the agglomerative clustering. I will pause for 1 minute. If you have any question, you can ask now. Okay, since I do not see any question, we will move on to the next problem. Next, we will solve some problems on agglomerative clustering. The single linkage, complete linkage, average linkage, all these algorithms we will see. So, the first question is, for the following points, agglomerative clustering with single linkage is used to cluster the data points into 3 clusters. Determine the clusters. So, here you have agglomerative clustering with single linkage. So, when you have single linkage, then while determining the distance between 2 clusters, you will have to take the minimum of the distances of all the pairs of data points, where one data point in the pair is from the first class and the other is from the second class. You will have to consider all those combination distances and you will have to take the minimum distance of these finally as the distance between the 2 clusters. That is your single linkage. Now, how the algorithm works? So, first here you assume that here you have 7 data points. So, initially you assume that all the data points belong to different clusters. So, you initially have 7 different clusters. Now, you see what is the distance between each pair of clusters, and the one that is having the pair that is having the minimum distance, you merge those two and you form a new cluster. So, now once you merge 2 of the clusters, you will have 6. Now, you have 6 clusters. Again you do the same thing, but this time you compute the distance while considering the merged 2 data points as one cluster. This way you keep on merging, and since here it is said that you need 3 clusters. So, once you got 3 clusters, you will stop, but otherwise you can keep on going for the entire process. You can keep on going until all the points are coming into the same cluster, but here we will stop when we get 3 clusters. So, for this the first step will be to compute the pairwise distance between all the data points. Okay. So, let us do that. So, we have 7 data points. And the points are 1 1 1 2. Let me write it here for convenience. So, these are the 7 data points. Now, the distance between A and A is not important. We will first consider the distance between AB, that is the Euclidean distance between AB. As you can see, the distance will be 1. Now, between A and C. So, if you consider A and C, the distance will be, let me compute the distance. Okay, I will just pause for a minute and bring the calculator to do the calculation. Just a minute. I am sorry for the inconvenience. I am sorry, guys. Okay. So, we are computing the distance between A and C. So, the distance will be will be 3.6. If I make any mistake in computing these distances, please tell me. Next is A and D. So, that will be 4.2. Next will be 5.9. Then between A and F, it will be 5.4. Then A and G will be 5.6. It is 7. 5.7. So, this first row will also be the first column. So, just let us write that. Now, we will compute the distances with B. So, the distance between B and C will be 3.2. Then B and D, that will be 3.6 again. Then B and E, .8. Then B and F, 15.3. Did I do it correctly? 3.5. Yeah, sorry, I did it wrong. Wait, let me check. I may have made a few mistakes in this. Let me check once quickly. Six. With A these are fine, with B this will be this will be 5.9 again. Sorry. This is E, so the first difference is 5, the square is 25 plus this one we are considering, so second one is 2.2 square, this will be 5.5. Now the next one will be .6. The last one will be 5. This will be same in the second column. CC distance is not important, then we will compute the distances with C and C with C. So CD, the distance is 1, C and E, the distance will be 2.3, C and F will be 2.5 and C and G will be C and G will be 2, 1, 2. Same this side. Now we are considering the distances with D. D and E. D and E, the distance will be two. Then D and F, the distance will be 1.5. Then D and G, the distance will be 1.4. Same this side. Now with E, the distance between E and F. So the distance between E and F will be 2.4, and E and G will be 1.3. So 2.4, 1.3, and F and G, that distance will be 1.1. So these are the final distance matrix. Now we were told that we need to use the single linkage and the agglomerative clustering. So here in this distance matrix, first you can see that the minimum distance that we have for step 1, the minimum distance that we have is this one. This one is the minimum distance that we have got. So at step 1 we can merge A and B together, and the remaining will be as it is, C, D, E, F, G. So you will have to now form a new distance matrix where AB will be treated as a single cluster. So let us do that. I will try to do it here only. So AB is together, I am writing it as AB. Now when computing, you are using single linkage, keep that in mind. So when computing the distance between any cluster with the cluster AB, you will have to take the minimum of all the pairs of distances, where each pair is formed by taking one sample from the cluster AB and another sample from the other cluster. So first, when you are trying to compute the distance between the cluster AB and C, so you will have to compute the distance between AC and BC. AC and BC, which are these two, and you will have to take the minimum of those as your final distance. So it will be 3.2. Similarly, when you are computing the distance between AB and D, you will have to take the distance AD and BD and take the minimum, which will be 3.6. Similarly, you can fill the remaining. E will be 5.5, F will be 4.6 and G will be 5. Similarly, this side. Now the remaining were the same as before, so we can simply copy those. So this was step 1, this is step 2. Now this is the new distance matrix. Here also again you will have to take the minimum distance. Again that is 1 and that is between C and D. So in the next step you will join C and D in one cluster. So in the next step you will have AB as one cluster, CD as one cluster and EFG separately as before. Now you will have to again, so now you have got 5 clusters. Your aim is to get 3 clusters. So again you will have to do the same step. Now you have to compute the distance between cluster AB and cluster CD. So if you see here, you have to compute the distance between cluster AB and cluster CD. So you will have to compute AC, let me mark it in some other color, AC, AD, BC, BD, all the 4 distances, and you will have to take the minimum of these 4, which is 3.2 in this case. So your distance between AB and CD will be 3.2. And the distance between AB and EFG will be the same, 5.5, 4.6 and 5. Now you have to compute the distance between cluster CD and cluster E. So you will have to consider the distances CE and DE. So the minimum is 2. So this distance you will get as 2. Now CD and F you will get 1.5. CD and G you will get 1.4. Then between E and F, E and G. Lastly, F and G. So this is the new weight matrix new distance matrix in step 3. Now again you will have to take the minimum distance. So as you can see, the minimum distance is now 1.1. So that distance is between F and G. So in the next step you will merge F and G. So the next set of clusters that you will have are AB together, CD together, E separate and FG together. Okay. Now you have got 4 clusters. You will have to do one more step to get 3 clusters. Let us do that last step. So between AB and CD it will be the same. AB and E will be same. Now you have to compute the distance between AB and FG. AB and FG. So the minimum will be 4.6. This will be 4.6. CD and E is 2. CD and FG, it's 1.4. right, 0.4, and E and FG. So E and FG, it will be 1.3. So now you see the minimum is 1.3, that is between E and FG. So in the next step we will combine E with FG. So the clusters you will get are AB in one cluster, CD in one cluster, EFG in the third cluster. So this is the final clustering that you have. You have 3 clusters now, so you will stop at this point. This is how you do single linkage, that is when the distance between 2 clusters you are computing by the minimum distance between the pairs. Now the next question, we will do that as the last problem for today's session. This is the same data points that you have in the previous question. Again you will have to do agglomerative clustering, but this time you will have to use complete linkage. So in complete linkage what you do is you take the maximum distance in order to determine the distance between 2 clusters, maximum distance between the pairs. So the initial step 1 distance matrix will be the same because you have the same set of data points. So I will write the answer for this in a different, for complete linkage in a different color in the same matrices, so it will be easy to compare. So let me use the red color. So the step 1 will be the same because that's just the distance between each individual points. So that distance will be the same. So the minimum will again be the same. So you will get AB together. That is same. So AB, then you have CD, E, F, G. Now when you are computing the distance between AB and the other clusters, there the difference will come. So let us say you are computing the distance between AB and C. Okay, AB and C, that is you are considering these two distances. When you did single linkage, you took the minimum of this, but for complete linkage you will take the maximum of this. So this distance will become 3.6. Similarly the rest, this will become 4.2, this will become 5.9, this will become 5.4, and this will become 5.7. Similarly on the first column. So the weight, the distance matrix that you have, that will be different. But you see the remaining entries, which are again distances between individual elements, those will remain the same. So only the first row and first column will be different between the single linkage and complete linkage. So here again your minimum distance will be 1, which is between C and D. So you will again merge C and D as you did for single linkage. So now you have AB together, CD together, E, F, G. Now when you compute the distance, first you have to compute the distance between AB and CD. So now you are considering AB and CD. So these 4 distances you are taking into account. And last time you took the minimum of this, so you got 3.2, but then now you will take the maximum, so you will get 4.2. This will be 4.2. AB with EFG, those will be 5.9, 5.4, 5.7. This will be the first column as well. Now when you are computing the distance between CD and E, so you are taking CD and E, so you are taking these 2 distances. So last time you took minimum, so you got 2, now you will get 2.3. Now this is 2.3. Similarly the other 2 will be 2.5 and 2.2. 2.5 and 2.2. The remaining distances will be the same because those are the distance between the individual elements. those will anyway be the same. Now if you see the minimum, you see this time also 1.1 is the minimum. So again you will combine Fg together. So you are combining the same things together, that is alright, but the distance matrices that you are getting in each step, those are being different. So let us see the last step for the sake of completeness. So now you have merged F and G. So you have AB, CD, E and FG. Now the distance between AB and CD, as we have computed, is 4.2, AB and E is 5.9, and AB FG, that we will have to see. AB and FG, the maximum distance is 5.7. This will be 5.7. Then the distance between CD and E, you had 2.3, so this will be 2.3. Then CD and FG, so CD and FG, it will be 2.5. So you see that the distance which was 1.4 is now 2.5. Now EFG, E with FG, this distance will be 2.4. Okay, so this distance is 2.4. Now you see the minimum in this is now 2.3. This is the minimum distance, which is the distance between CD and E. So with single linkage, your clusters were this. Now with complete linkage, your clusters are AB together. Now the minimum distance you have got is 2.3. That's correct, right? Yeah, 2.3 is the minimum. So 2.3, that is between CD and E. So you will merge E with CD and you will have another as FG. So the E element is belonging to two different clusters in case of these two types of clustering algorithms. So this is how you do agglomerative clustering using single linkage and complete linkage. So this is what we had for today's session. If you have any questions, you can ask. Okay, since I do not see any questions, so let us stop today's session here. Thank you guys for joining. We will meet again in the next week.